The answer is a man, Alexander Papaderos. A doctor of philosophy, a teacher, a politician, a son of this soil. He came to believe after the war that the people of Germany and those of Crete had much to learn from one another, much to give to one another. For if they could forgive each other, then anybody on earth could.
Well, Papaderos succeeded. The Institute became a reality, a conference ground on the site of horror, and a source of productive interaction between the two countries. When I came to the Institute for summer session, Alexander Papaderos was already a living legend. One look at him, and you saw his strength, his intelligence, and his passion.
At the end of the last session of a 2-week seminar, Papaderos rose from the chair in the back of the room and walked to the front, where he stood in the bright Greek sunlight coming in through an open window and looked out.
We followed his gaze across the bay to the iron cross marking the German cemetery. He turned and asked,
"Are there any questions?"
Quiet quilted the room. These last 2 weeks had generated enough questions for a lifetime. But for now, there was only silence.
So I asked the question, Dr. Papaderos, what is the meaning of life?
The class laughed at the absurdity of the question and stirred to go.
He raised his hand and stilled the room.
I will answer the question.
And he reached into his pocket and took out a very small, round mirror. And what he said went like this.
When I was a young child during the war, we were very, very poor and lived in a remote village. One day on the road, I came upon the pieces of a broken mirror. A German motorcycle had been wrecked in this place.
I tried to find all the pieces and put them together, but it was not possible. So I kept only the largest piece, this one, and by scratching it on a stone, I made it round. I began to play with it as a toy and became fascinated by the fact that I could reflect light into dark places, into deep holes and crevices and dark closets. It became a game for me to try to reflect light into the most inaccessible places I could find.
I kept that little mirror as I went about my growing up and would take it out from time to time in idle moments and renew the challenge of the game. As I became an adult, I realized that this was more than just a game. This was a metaphor on what I might do with my life. I realized that I was not the light, nor was I the source of the light, but the light,
Truth,
Understanding,
knowledge,
is there and will shine in dark places only if I reflect it.
I am a fragment of a mirror, whose whole design and shape I do not know. Nevertheless, with what I have, I can reflect the light into the dark places of the world, into the dark places of people's hearts, and change some things and some people. Perhaps others will see and do likewise. This is what I am about. This is the meaning of my life.
And he took the mirror and holding it very carefully, caught the bright rays of daylight streaming through the window and reflected them onto my face and onto my hands folded across the classroom desk.
Are there any questions?
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 There's no way to measure what these fragments are worth. Scattered moments of connection to life on this earth. Flashes of understanding that can set your soul ablaze and flicker softly through all of your days. Stop now and listen. Can you hear a faint melody just outside here, all around us? A great symphony. But nothing in life has the power to inspire. By guiding your eyes to the mighty fire. How can we live in the dark when we could be part of that light? That light. How do we capture that spark and reflect it into the heart of the night?
Let's move in on sound and voice. And who to the light? Our stage manager, Elvis Gary Dave.
Joe Mason, our director. On video.
Thank you all for coming.
All right.
That's converted to useful work. In the cycle depends upon what? In the engine, primarily the expansion ratio. That is the compression ratio, and the indicated thermal efficiency varies as the Otto cycle efficiency, 1 minus 1 over R to the K minus 1. Right? That's the number one thing, isn't it, that determines the power. And heat transfer loss from the cylinder, or from the gas, during combustion and expansion. Those are the two things, aren't they? That's what determines it, isn't it? The expansion ratio, and how much energy I lose during combustion and during the expansion process. We should have known that, shouldn't we? We stop and think about it. If I talk fast enough, I can sometimes get you to follow along with the other arguments, right? Okay, if this is the case, and obviously the heat transfer during combustion and expansion is important, because if you lose it during combustion, lower pressure and temperature at the start of expansion, lose it during expansion, you have lower pressures and temperatures along expansion, and we get less work. If this is true, then why do we see a lot of interest in adiabatic engines? With an adiabatic engine, we insulate the cylinder, the piston, heavy ceramic piston or something like that. We insulate the ports. We insulate everything, okay? We insulate the cylinders, the ports, the pistons, the head. Anything you can insulate. Since our work is determined by the heat transfer, it goes up slightly. But the big thing is the expansion ratio. We've got a limited expansion ratio for CI engine, maybe 16 to 1 or something, for typical engines. So what does this gain us if I insulate the engine? I get very high T exhaust. If I get very high T exhaust, besides throwing that away, what can I do with it? I can use it to run a turbine, which is turbocharging. So it compresses the air into the engine, increases the mass, increases the inlet density. But we'll see that if you have an adiabatic engine, you have such high exhaust temperatures that you can't use all the energy in the turbine for the turbocharger. So what you do is you use the leftover energy to what they call turbo compound. Okay, the engine. What this is, turbo compounding, is basically something like this. Here's my adiabatic engine. Here's my shaft, my flywheel sticking out way too far. Okay, here's my inlet. Here's my exhaust. Okay, so I have then hot exhaust gas. I will use this gas. Here's a turbocharger compressor. Air coming in. Okay. And then I drive that turbocharger with a turbine. Okay, so this is the compressor, and this is the compressor turbine. And together, this is the turbocharger. Okay? So if we just have a turbocharged engine, that's basically what we're doing. Use the exhaust gas to drive a turbine, which drives the compressor, which compresses the air to go into the engine. Okay? Now, since we have very high temperatures, we have a lot of energy left over. Okay, so the temperature here is still high. So what do? Well, what I do is I put another turbine in here, which is the power turbine. Okay, and I'm just going to kind of draw this schematically to show it's still sealed up, to extract energy from the exhaust gas. Now, turbines run at very high speed, so we're going to have to gear this down some way, usually through the front valve train of the engine, to flywheel speed. So these are different gear sets, okay? So what I do is I have a turbine, and I gear it down to flywheel speed. So I extract energy from that hot exhaust gas so that I can get more power out. Okay, and I can use this hot exhaust gas I'm generating. If I insulate the engine, all I do is generate a lot of hot exhaust gas. And I can't use all that energy in the turbocharger. So I either throw it away, or I turbo compound it, where I have essentially a gas turbine, which happens to be your exhaust gas, with just a turbine, no fuel added or anything, driving through a gear train to the flywheel. You see very often on the front train of the engines. Example of a non-insulated engine, 375 horsepower, brake horsepower size. There was something on the order of 50 horsepower floating around on that turbine shaft that they could extract. It's a very highly turbocharged, non-insulated engine. So there's a lot of power to be realized. Basically, what are we doing by turbo compounding? What are we doing by turbo compounding? We're messing with the expansion ratio, aren't we? We're increasing the expansion ratio. Okay? We can only expand it so far through this turbine and get power out. There's still power left, right? So basically we could say, we could sketch it kind of like this. It's not exactly right, but it's kind of useful. Here we have compression, combustion, expansion, blowdown, exhaust, inlet. We've only expanded down to this pressure, right? Okay? I would like to expand it further. So basically what I'm doing in the turbocharger turbine and in the power turbine is I'm continuing this expansion on down to something approaching atmospheric. And maybe this part is the turbocharger turbine, and this part will be the power turbine. Okay? We're increasing the expansion ratio. It's closer to a complete expansion engine. The Lenore cycle from way back when. Tried to have complete expansion. Okay? That's one way of doing it. It's turbo compounding. Okay? That's why insulated engines. It's a good time to talk about it when we talk about heat transfer. Okay? So what do we need to remember is summary. Okay, what do we need to remember as far as what we're going to need for our performance discussion? Well, besides using the equations for the heat transfer, we need to remember that for SI and CI engines at what we call full load or rated or the wide open throttle if you're talking spark ignited engine at a variable speed, the percentage heat transfer loss decreases as speed increases, so the indicated thermal efficiency increases. And this is all because of speed to the 0.8 power, or Reynolds number to the 0.8 power, or piston speed to the 0.8 power. And for SI and CI engines, at constant speed, variable load, which we said we got the same answer for different reasons, the percentage heat transfer loss decreases slightly. And we said maybe fairly constant for the CI engine. Therefore, the indicated thermal efficiency will increase slightly, or maybe really constant in the CI case. Okay. We got essentially the same effect, same answer for different reasons. So it's going to increase slightly or maybe be constant in the case of the CI engine. Okay? So now you can take a look at problem set 7, engine heat transfer. Okay? And calculate the heat transfer, the heat load, the heat transfer for the engine. Okay, now let's take a look at something we're going to start today, then we'll finish up with a little more detail and talk about a good deal tomorrow, next period rather. Valve timing. The next variable we said had a big effect on performance. Valve timing for 4-cycle engine, or we could say port and or valve timing for 2-cycle engines, okay? Let's talk about valve timing. Reading the book, and we know from other thermo and everything, for the ideal engine, what do we have? Instantaneous actuation of the valves at top dead center and bottom dead center. Bingo, they're wide open. Bingo, they're closed, right? Well, obviously, we can't achieve that.